to live. Yeah, we are on live. Okay. Yeah,
Govin,
sir.
good evening, Govin. You can
Sir,
start the
good evening, sir. Yeah, good evening, sir.
you start the video streaming now only. YouTube
Yes,
streaming
yes.
you start now only.
Yes, it is started,
Takes
sir,
some
already.
time. Okay,
Yeah,
okay, good.
yeah. How many participants?
I think we can start going. Good number is there.
Okay, sir. Yeah.
Or else if you want to wait 2 minutes, you can give.
Yeah, that's right. Till it is double digit.
It's look like chain only. We don't unable to see the number.
We are monitoring in separate screen. Internet.
You can start going. More than 40 are there.
Yeah. Very good evening, participants. Welcome to day 2 session 2 talk, this FTP program. So now I welcome Mr. Chaitanya Kancharla, Design Verification Engineer at Intel Corporation, Bangalore, to this session. Chetu, please welcome to this session.
Hi, Govind.
Hi. So Chetu has good exposure to verification at IP, subsystem and SOC, subsystem at SOC level, worked on VMM, OVM and UVM methodologies. He worked on Ethernet, fiber channel, video peripherals like I2C. He developed VIPs from the scratch, developed test benches using Verilog, HDL, System Verilog with UVM, C and C++. He is currently with Intel Corporation Bangalore as IP verification lead from 2018. Earlier, he was with MediaTek as staff engineer and Marvell Semiconductors as senior engineer, IBM Technologies and hardware development as IBM Technologies and hardware development as staff engineer. He received his PG degree, MTech degree from NIT Trichy and BTech degree from MEGR College of Engineering. Once again, I welcome Chaitanya Kancharla to take over to this session and request him to take over the session. Please welcome Chaitanya.
Yeah, thanks. Hello. Yeah. Thanks, Govind.
Thank you.
Today I'm going to start this session basically on the trends in VLSI and modern verification techniques My experience is mostly in RTL design and verification. So this presentation will mostly focus on RTL design and verification techniques and what are the recent trends in the chip design. Just a disclaimer before we start this presentation. This presentation is being made on capacity of an individual and it has no relation to any organization. Yeah, I'm just starting over.
Please go ahead. Yeah.
Yeah, agenda, I would like to focus on these areas. Basically, I would like to start with industry product focus, means how is the industry products are classified, and the industry trend of SOCs and the design reuse, followed by the design verification scope, and then the verification impact on the time to market. And I'll conclude with bottlenecks currently we are facing in the verification area, and also the research areas which any interested individual can focus on going forward. Yeah, going to the next slide. As I said, current VLSI industry product focus, you can classify basically into these 5 areas. If you see any company that is working or any most of the research organizations or anything, we can classify into these 5 areas. So the first area being the ASIC and SOC design. We all know that the products we use in daily day to day are all basically some kind of an ASICs or a system on chip. Okay, and so that is the main category, and that's where the volume of the market is currently focused on. And next thing is the FPGA design. Even though ASICs and SOC markets have been volumes have been more, but FPGA design from the starting has been the backbone in implementing various prototypes as well as areas where we wanted applications like DSP and all those things, FPGA design, where the frequencies are slightly lesser. FPGA design is completely unreplaceable. That will be the second area. And third area, since it's a billion market and we need designs which are to be at a faster pace, we need a good EDA tools. So there is a heavy investment and then heavy expenditure in terms of the EDA tools. So that is the third pillar we can say. And the fourth one comes the manufacturing. Actually, without manufacturing, we don't have the other ones. So as the transistors shrink and the gate lengths become smaller, manufacturing at smaller nodes, fabrication and all is going to be the challenging part of going forward for the VLSI industry. So that is the fourth pillar. And the last, it's all we have ASICs or SOCs, anything, but we still need to bring up. So we need system design, we need to do product validation, we need to do the board design, and then finally we have to give it as a product. But if you take the first 3 ones, we can split into front end and the back end. Front end, we do have simple microarchitecture to synthesis and the STA, and the back end we do the layout, routing, and DFT, BIST scan till the GDS2. And so that is a broad classification. And if you take any of the companies, you can map into one of these verticals. Okay, going to the next one. I'm going to start with a basic slide. This is like a process or a technology node. Why I'm starting with this slide is because this is the driver for entire VLSI. So everything is based on this chart. Currently, if you see, these are all on the left-hand side, we see all the fabrication companies. you could see all these are constantly working on fitting more number of devices or more number of logic into the particular chip or particular ASIC. So you see, in 2013 we can see it's like around 28 nanometer, but around 2019 we are closing on to 5 nanometer or 7 nanometer plus. 5 nanometer is still in work in progress, but if you see 7 nanometer is the we have seen some chips already being released in 2020, which are 7 nanometer based. So if you see, we are as 7 nanometer is like we are putting more and more logic, we are putting more and more computation, we are putting lots of efforts because 7 nanometer is not like we can't go for every other thing. 7 nanometer we need to go if we can pack that much logic, otherwise the cost effective manner will not be, volume and cost effectiveness will not be achieved. So if you see all these nodes, it's just almost every year we see the nodes changing. So that means that much of workload we have in terms of verifying the chips or designing the chips or getting the best out of it. And the other important part with this is like, even though you see that 7 nanometer is like a product which has come in 2019, but to sort out all the yield issues, like unless you have a very good yield, like around 90-95%, we cannot really justify the volume or the price we pay for the ASIC or an SOC. So if you see all these things, it's mainly driven by the volume and then the process at which each customer demands. Like, for example, if the customer's requirement is towards a very high computation, low power dissipation, and then he has to put in lot of logic inside it. So that's where we have to go for the higher technologies, like 5 nanometer and 7 nanometer. Okay, so that this is a driving factor for all of our production as well as entire industry, and that is where our Moore's law are while are the driving point of all our industry are following the Moore's law. Okay, and going to the next slide, what are all the driving factors? Why we need to have better? Why we are going for a better technologies or better SOCs because of all these driving factors. So first thing is we are getting better transistors. We are seeing every day a lot of people are researching on these transistors to reduce the power consumption and then reduce the leakage currents, give better transistors. We can think something like 3D FinFET, FDSOI, etc. And second point being the higher radio frequencies. Here we have seen in 2020 we are progressing towards 5G, and also so higher the radio frequencies we need to the RF logic becomes bulkier. So that is where we need a very complex technologies like 5 nanometer, 7 nanometer. And now we are seeing AI as a driver of the market. AI and machine learning are pushing every company and every vertical. So we need, for AI to succeed, we need better parallel processing. So if we need better parallel processing, our multi-core or octa-core processors may not be enough. So we need better parallel processing for the accuracy of the AI systems. So that is where we are driving, industry is driving towards these technologies. And the other side of applications we have is a RAS related applications like reliability, availability, and serviceability. We want our products, for example, other than mobile is not in our RAS related features, but other than if you take banking related servers or where serviceability is a main issue, like we cannot let the system down. So that is where we have more that is where the demand is towards always on systems. That is where we have to switch between multiple cores if one of the thread or one of the core is having issue. So that is where we need to pack more than one multi-processor or multi-core related logic into the chip. So that is another driving factor, and fault tolerance and recovery. So we can see bit errors as technologies are going downwards. We can see bit errors. There are a lot of faults that can be injected because of the yield issues, or because of technology issues, or because of any IR drops, anything. So we need a mechanism with recovery and fault tolerance. So those some of these things are also driving. And the next thing is the customer requirements. Day by day we see that customers requirements are also increasing a lot. So till yesterday we have seen 4K TVs. Now maybe next year we'll be seeing 5K 8K TVs. So so that means better protocols, better systems to support these kind of displays. So that's, and also you see the protocol improvements. See, and also these are all because of the speeds. You see, for AI we need much higher speeds. So the old protocols like USB 3 or USB 2 no longer are sufficient. So we are industry is working towards USB 4 and all other higher speed SerDes protocols like PCIe 6, DisplayPort, and HDMI higher versions. So all these are driving us because of higher speeds, and also the availability of better cores. You see, ARM comes up with every quarter they come up with a better Cortex core. They come up with multi-thread, more number of cores, more better power consumption, and then the lot of features like floating points, sub number of parallel floating points that are supported. All those better processes availability are coming even every quarter. So that's why you see a lot of companies like AMD, Nvidia, Intel releasing a lot of cores and graphic processors for better computation. And also, just the speed is not enough, but we need better memories. So even the DDR protocols are coming with much higher frequencies and much higher speeds. So DDR 5, 5, 6, 7, and also an LPDDR, which is used for the mobiles. We are getting a release almost every 6 months. So the customer requirements, the demand, everything is moving towards us, towards better technology, and then better uh, high speed of the ASIC or an SOC implementation. Okay, so these are the driving factors now. Because of all these things, now we need to spend more time in not only designing but also in the verification of the particular ASIC or an SOC. So I'll just take from the vertical point of view SOCs as a market focus, and we'll see how SOC is driven from here. So as you see, SOC is a system on chip, and where it's a collection of multiple IPs. So, and IPs, we can classify it as both soft IP or a hard IP. And once we have a IP, we start building up as a basic building block, and we start defining our SOC. Just to clarify, the soft IP, when a company delivers a IP in a Verilog or a VHDL functional model, and it's the company's and the current company's synthesis flow is used, then that is a soft IP. But when a company delivers it as a hard IP, means you can directly map it to the GDS2, and you can take it to the process technology directly. Means you cannot do any modifications for the hard IP. Hard IP is generally process dependent. So if you are if you are getting for a 7 nanometer hard IP, means you have to use it for a 7 nanometer, and you cannot change anything in it. But soft IP is where you can it's a functional model based on Verilog. So during the synthesis, you can use it as per the recommendations from the from where IP is owned. Okay, going to the next slide. I'm just classifying here what are soft IPs and what are hard IPs. So mostly, if you take from any application point of view, any controller, for example, Ethernet MAC controller or a DRAM controller or a PCIe or a USB, any controller will mostly be in a soft IP, complying with the specification. So like for example, if you take USB, if you take a 3.2 spec, so then it will be the controllers will be a soft IPs based on 3.2 spec. And that is where the soft IPs will be delivered to the company which is going to integrate the SOCs. And also our most common example is ARM Cortex IPs. So we get the ARM IPs and then we integrate into our flow, and that is where we build our SOCs. And their ARM has a lot of AMBA IPs like AHB, AXI, and also most of these are coming as soft IPs. And as I said, there were now we are trending to 8K displays, and also all the display controllers from any companies will be getting as a soft IP. Hard IPs are mostly which have relation with certain analog world, so that are mostly being categorized as hard IPs. If you take any analog and mixed signal logic designs for SERDES, like or PLLs for the frequency generation, ADC, analog to digital converter, or a digital to analog converter. So all these have analog content. So that is where they are more tightly close related to the process node, which with which you are going to fabricate your SOC. And if you take all these protocols, the physical layer is definitely going to be having a serializer, deserializer. So that is where mostly all of these come as a licensed hard IPs. And in case if you change your technology, you again need to procure a hard IP based on the technology. And these are hardly reusable because of the technology dependency. Okay, so these are a few examples of soft and hard IPs. Yeah, going to the next slide, I'm just trying to give an example of a cadence soft IP and a hard IP. Now, if on the left-hand side, if you see this, this is a PCI controller. So on the top, if you see, it's the what we can say is a north side. North side is could be any it could be any bus. You can integrate if you are using an AMBA processor or an ARM processor. You can have an AXI bus, or if you have your own processor, then you have your own custom bus. You can have a bridge over this, like your custom bus to AXI bridge. So this IP comes with the AXI on the north side. On the south side, it has the pipe interface, like it's a PCIe interface. So this comes as a total soft IP. So it has a configuration registers and all the as per the PCIe protocol. So all the transaction layers, link layers, and the digital part of the physical layer, like LTSSM state machines, all this will be a part of the soft IP as per the PCI protocol you're using. So it is basically dependent on the spec version, specification version which you are complying. But on the right hand side, if you see, this is the hard IP. So this is where you have the serial to parallel converters and parallel to serial converters, and feed forward equalizers, based PLLs for accurate frequency generation. And so all these analog related components which are driving the RX and TX pads. So these will be the hard IPs. So these are from the vendor cadence. So this is so based on your requirement for your SOC, you have to procure them. Okay, going to the next slide. Since now we are talking about the SOC and the design reuse, now as we see, right, we have sort of soft IPs, hard IPs. Now we are planning to build a SOC. Now, for all the requirements, we have DSPs coming as soft IPs from probably from Texas Instruments, microprocessors from wherever one you want, and certain encryption related blocks like AES and all you have and certain blocks. And then you have your own custom designs you wanted to integrate, which are very core specific for your application. Now we have reused all these things and we have made it into a complete SOC based on the IP libraries we support. Okay, going to the next slide, I am just showing a particular example of how an integrated SOC looks. You can see DSP cores, you can see ARM cores, you can see on-chip memories, you can see memory slots for the DDR or whatever those things. So a typical SOC after it has been integrated with all the soft and hard IPs will look like this. So as you can see now, it's a very huge complex chip. So just by integration of these IPs, we can't achieve anything because that's where now our focus of verification comes into the picture. Since there is a lot of design reuse and a lot of IPs coming from multiple vendors, so some of the IPs are coming from internal, some of IPs are coming from external companies, some are coming from standard companies like ARM. So there is a lot of asynchronization within the SOC itself. So one verification methodology or one verification may not be really be suited to give a first time working silicon. So that is where verification is going to be a major challenge because of the driving factors of the technology integrating lots of chips, lots of IPs, and then we have to verify each and every IP to get the proper functionality of the SOC. Okay, yeah. So now I'll just, this is a common design chart, but I'll just put this from the verification or validation point of view. So now your concept of or market requirement of an SOC has been obtained. Now you as a designer or you as an architect will get the concept into a RTL design. So that is where they run through the behavioral specification. There will be a lot of C modeling. There will be MATLAB simulations. There could be any proprietary based also. So there could be lots of things during this step before we really see an RTL design, because RTL design is where we are like almost finalized on all the specification. But before RTL design stage comes, we have the concept to behavioral synthesis is where a lot of specification evolution happens. For example, I want a SOC which can support USB 4, or it can support PCI Gen 6, or it has to support a display which is a 4K or an 8K. All the specification, total latency numbers or total bandwidth numbers, all those things will happen at this stage of the design. So that is where once you have the required numbers, so that is where your idea will go into an RTL design. But so from behavior to RTL design, again, we do certain RTL verification to validate. And for concept to behavior specification, there will be a design validation. Mostly this will be a proprietary based flows based on the complexity of the SOC. And once RTL design is there, it's all a generic flow of netlist layout, DRC layout, manufacturing, GDS2, everything. It's like a standard flow. So, but at every point you see there is a verification which has to clearly give that the intent at the first step to the intent at the last step is met. Okay, so that is the idea of totally verification here. And so just to explain it in another way, in this slide, I'm just putting what are the design transformations and how the design transformation is being supported by verification. So now you see we are going from an idea, algorithm, spec, RTL, gate, GDS2, ASIC and product. So all these are steps, but all these are kind of a transformations where an idea gets over. So, but these transformation have to be verified at each and every step. That is where our verification becomes a bottleneck of the total SOC flow. Okay, so that is so if you see, as I said, there could be some C models to verify from idea to algorithm, and then there could be some spec acceptance reviews or behavioral models, and it flows through the simulation code review, and a verification criteria have to be satisfied here, and then there will be a timing sign off, and then there will be once your ASIC is out, they need to be qualified at the automatic test equipment generator, and then at the end product you need to have a product acceptance test to for the SOC to be finally being qualified as a perfectly working silicon. Okay, so now we have seen the complexities of the SOC. We have seen what is driving the SOC, how much complex it is. But now, if you see, if a silicon is not working, if your SOC is not working, so if you classify this, what are all the failures with which a silicon is not working? So this is a data which I just got from one of the companies, one of the company site. So its data may not be 100% relevant, but the numbers are really effective to explain what is the effect actually. If you see, of all the chips that have not been working, so most are around 77% have been failed because of a logic or a functional bugs, because we could not what has been what is the specification, what is the output is not been clearly met. So that is where 77% of the failures have been classified. And second point is where the clocking. Now you are integrating an ARM processor or a Cadence VIP or Cadence IP or a PCIe bus or so many things you're integrating controllers, you're integrating so many things, and each of them operate at different frequencies. So your processor operates at a higher gigahertz frequencies, but your memories may not be that faster. So there are a lot of asynchronous domains here. So the next part is the async domain crossings. That is where the failure rate is more dominant. And the next point is where the analog circuitry. As I have shown you in the hard IPs, there are a lot of PLL blocks, analog to digital converters, and a lot of parallel to serializers and serial to parallelizers. So, and most of these are technology dependent. So if any issue is there with respect to the technology, then we are going to have a dead silicon. So that is where the next set of problems come. And these noise factors are mostly with respect to the analog one. We'll skip this. And power consideration is the most important in today's technology world. We have been seeing most of us being using mobiles and all other hand peripherals are going to be the driving the VLSI industry. So any power consumption which is out of the specification is seriously going to hurt us. So if you are saying my power budget is 1 watt, you should definitely stick to 1 watt or 1 milliwatt, whatever. So, but if you are violating even by 10%, then I think your SOC or an ASIC is not accepted and it cannot go into a volume manufacturing. And that is why power verification or power is very important in today's designs. The next we we are going for mixed signal or some other. These may not be very much critical at this point of time, but these are mostly specific to a mixed signal or technology problems. And if you take the first left hand side, problems are basically when you think it was on a settled node. What I mean on a settled node is, suppose now TSMC is manufacturing a 5 nanometer chip. So you can't expect these things to be a main problem, because there most of the problems will come into the yield related things, because 5 nanometer to come to the that yield of 95%, it takes 1.5 year. So currently these data we will assume maybe on a 14 nanometer or a 10 nanometer, which is kind of settled at this point of time. So once we assume that node is settled, and still we still have some 17% yield issues. So that is where currently these are the factors which are affecting the ASIC and SOC. Okay, so and also this chart highlights the importance of verification and its a critical path in the delivery of the SOC. Okay, the next one. So now I'm going to deep dive into RTL verification or whatever. It's not only RTL verification, the complete verification, where you see that 77% of the product failures can be avoided. How and what are the layers of verification we do, and at what all levels we need to do a verification to get a perfectly working silicon. So if I can classify at the first level, so I can say it is a IP or a block level verification. So I mean, we know, but most of the time SOCs are built with blocks from other IPs, but many companies in order to do cost saving, they have their own IPs, unless it is like a very cutting edge IP. Like if you think we have USB 3 currently 3.2 being used in most of the laptops or most of the mobiles wherever it is. So that is not a cutting edge. So that each company can have their own IP. But if you're going for a cutting edge, maybe you need to get it from some other company. So block level or IP level verification is where we have the first level of verification being done. And once you have a block and you can integrate it into another block like controller and a file. Controller and file, you merge both of them and you run a verification environment, and you see whether both the blocks are talking perfectly. Like if you say this is compliant to one specification, this also should be compliant to the same specification. So if they don't comply, or if the traffic, if the data traffic that is going doesn't match, then those kind of issues we can catch at the subsystem level verification. So then once we have the multiple subsystems being integrated, we will go into the SOC level verification. Like now each subsystems, like the subsystem where ARM, for example, you take an ARM processor. So all the IPs which are talking with the ARM have been verified separately. All the memory related IPs talking to the memory interface have been verified separately. Now we integrate all of them at the SOC. So that is where we do the SOC level verification. So now this is where the total SOC has been integrated, and we do the total verification. And the last step is the post silicon validation. So most of the time, if there are new technologies, like if you're going for the first time to 7 nanometer, or first time you are creating a new IP like PCIe Gen 6, or first time you're integrating an ARM processor. So most of them, they will have a test chips. So those test chips will also need to be validated. Like before going for for a huge production, we will be having a post silicon, like silicon, which is like a test chip, will be validated. So these are the basic steps where a verification caters from the specification to the end product. Okay, but now when I classify the verification at these levels, but each verification category again needs to be categorized for various domains to catch the issues. The first one being the functional verification. So, functional verification, as it name says, just the function is A plus B is equal to C. If somebody defines, is it currently being working like that? Yes or no? That's as simple as that. So those kind of things can be categorized into simulation and formal. So these are two techniques which I will be describing later. Next is the performance verification. So now you are designing an SOC which you wanted your bandwidth numbers or the latency numbers or anything which you wanted it to be a better. So you have to do a performance verification. So if you are saying my SOC supports 100 Gbps Ethernet, but is your SOC really giving that output? So how do you verify those? So those things are very critical if you're having a intensive bandwidth numbers or intensive latency numbers or performance critical SOCs if you are delivering. So those for that we have a performance verification. And so the next one is the power aware verification. Excuse me. Yeah, power aware verification. So now, as I said, we are working on towards lower power. Means we need to be power aware. So if we are not verifying, and if we are not getting a throughput, and if you are not getting a particular SOC design with the corresponding power budget, then means you are not you have not designed it with the mind in power, because now SOCs are using lot of techniques for power saving. So if you are not able to meet the budget of the power, then I think your SOC doesn't or may not be able to pass all the quality criteria. So we have to do the power aware verification. And the next one is, as I said, already discussed, we have a multiple clock domains. We need to do the clocking and clock domain crossing verification for all the asynchronous clock domains. So that is where this step is pretty important. And the next one is, since we have a huge amount of logic and different number of IPs, in each IP have their own features. So, but now how do we know which IP has a problem? Just in case if you are doing a validation at a silicon level, you don't know how much, where the real problem is. Just that silicon doesn't work doesn't mean I mean, it doesn't give any information. So, but you need to know at what point or at what IP that has a problem. for example, if you take ARM processor, so okay, ARM processor is transferring data from one interface to other interface. So now it started fetching data, but now it was not able to send output. But now where is it stuck? So how do we know? So at what interface, at what IP? So then we have certain logic called design for manufacturing or design for test related logic. So that logic we can probe using some product testers have some probes. So where you can visualize what is at what interface we have the data being transferred, or where what interface inside the SOC the chip is, or the ASIC or SOC is having issue. So that is so that verification also needs to be done, because of the 5 nanometer or a 10 nanometer technologies. This step has also been very critical. Now we are doing this many verifications, but all these are basically our simulation models. So which means simulation models run a bit slow, but we wanted to accelerate them. So the last two steps, FPGA prototyping or emulation, and hardware software co-verification are where we accelerate our current verification methodologies using traditional, not traditional, using a complex processors called as complex boxes. They called it as an emulators, or you can think it emulator itself as a complex system. Using emulators, we speed up the verification. I'll be discussing that at the later stages. So these many steps of the verification we have to do for correctly closing on, or correctly getting a working silicon. Okay, going to the next slide. So I will be going through basically what is a functional verification, and also what are all the verification methodologies here will be briefly described. Give me a minute. Yeah, sorry. Uh, Okay. Yeah. As I described earlier, functional verification, like is your design intent, like what you have designed, is it coming? It is working as is. So is it working as expected? How do you qualify your design? So there are basically two approaches for this. One is simulation based approach, and other is the formal based approach. Both are two different ways of verifying a design. So if you take a simulation world, so I can describe this blue color box as the design. You can take an SOC if it is a SOC verification. If it is an IP, you can consider it as an IP. So you have your design. Now you have to verify it. What are all for what is your design designed? So your SOC has been designed for some application. So what all it has been designed? So that has to be tested. So that the left hand side stimulus part is where you generate, like for example, if you say I'm going to support 100 Gbps. So you need to have a Ethernet generator at this left hand side, and you pump into the design. So now you will see, okay, am I really getting the throughput of 100 Gbps? So that will be done at the right hand side. So in simple world and simple description, is your design working as expected? So that is how you test, like you give the stimulus and you check the results. Okay, now, so now you have complex SOCs. So how do you verify? Is it so easy to verify this? And the answer, we all know, it's not so easy. So we need a complex verification environment. So this environment you see is basically a simulation based verification environment, and the black box, you can think it as a design. It can be the DUT, you call it as a design under test. So that is where our design is actually. Now we have the design under test and it is being connected. Now we connect this with all our interfaces. Now you say my design supports USB. Somebody says my design not somebody says, your SOC says it supports USB. It supports gigabit Ethernet. It supports storage SAS SATA, and it supports HDMI. So now how do you verify? So now you have an interface and you have your verification IP, which is called VIP. So for example, now your SOC or your DUT, called design under test, says it supports a USB. So now you have a corresponding VIP called verification IP of USB. So you integrate that VIP here, which is complying with the same specification. Suppose your SOC has USB 3.2, so you connect a verification IP which is complying that. Similarly for gigabit Ethernet and also for SAS SATA. So you integrate all the verification IPs now. So once you integrate, you drive the corresponding stimulus into the design. Now your design or your SOC is able to process the data. Okay, now it is sending out the data after it has processed. Now, how do I know that it is processing correctly? So then now you connect the outputs, connect all the outputs through through another interface that would be typically called a scoreboard or a checker. So that scoreboard will typically take the output from the SOC, what is the SOC is giving out, and also it will take the input from the verification IP, because it has to know, it has to compare what has been driven and what came out of the design to specify that the data that is coming driven into the design and coming out is correct. And also for doing this complex verification, we know that every SOC has lot of registers. So all the registers will be defined in some industry standard specification called IP exact. So now IP exact, all the models will be integrated into this model called register model. So now you have your register model, which has all the register description of all your IPs in a SOC. Now it knows, for example, you wanted to transfer data from A interface to B interface. So how do you do that? You give it to the instruction to the core or an ARM core or whatever core you have. So that instruction, how is it driven? It is driven by through some register writes. So those register writes will start initiating from interface A to interface B. So all those configuration will be done through these register models. And so now, since your verification, you are driving a lot of IPs and you're collecting the data, you're verifying whether the inputs are correct or outputs are wrong or whatever. There are a lot of scenarios being driven. But now, how do you know that you have verified? You have verified 100%. How do you know that your SOC is 100% verified? So that is where you have this database called coverage database. Now I say I sent a packet from USB and the packet came out over the SATA. or it went into the processor, or it stayed into a DDR memory. So how do I know this scenario is being exercised? So that corresponding data path related information is being stored into this coverage database. So once we see that the coverage database has all scenarios hit, like all the cases are being covered, then we can consider as the verification to be complete. And just to explain here, the what a VIP is. A VIP is the verification IP, which has all few other components like driver, monitor, sequencer, and a few other things. So basically, the combinedly all these blocks will give you the corresponding packet. For example, if you take a Ethernet controller, so this verification IP will be able to give you an Ethernet packet based on the interface, or based on the correlation or between all the blocks inside, based on the protocol. So verification IP also has to comply with the protocol with which the SOC is designed, so that we can verify the same intent is being designed in the SOC. So this is the simulation-based verification, where you can see you can use it for the verification. So basically, all this environment is being driven by a methodology called UVM, that is called a universal verification methodology, which is being now widely used across the industry, and it's an IEEE standard as well. So I will describe more about that in the upcoming slides. But for this point of time, you can see that simulation. These are all the interfaces we use, and this is how we verify the SOC. Okay, going to the next slide. Now we are doing simulation. So, but simulation, as the name suggests, it's kind of an simulator where it approximates the real world, but it's not really a real world. So there are limitations with the simulators as well. So, and there are different types of simulators. So you have to choose your simulator based on how your design is really being coded. Does it have an asynchronous interfaces? Does it have asynchronous clock domains? So based on that, you have to choose your simulators. For example, the most commonly used simulators across the industry are the event-driven simulators, where the design is being evaluated at each and every event, and mostly the designs will be based on flip-flops. So these are the event-based simulators. So from the industry point of view, if you take these companies, Synopsys has a VCS simulator which is used for this purpose, and Cadence has NCSim, and Mentor Graphics has QuestaSim. So these are all the event simulators which are commonly used across the industry for verification, to get the to verify the output, to verify the intent of the design. But there are other set of simulators also called as a cycle-based simulators, which do not evaluate each and every evaluate at each and every event, but they do evaluate only at the discrete time, like every cycle. So based on your application, these are mostly company specific, and based on very particular applications like latch based designs, these cycle based simulators are used. So most of the industry is being currently working on the event based simulators to verify those designs, but cycle based is also used only, but at a very limited scale on an application basis. So this slide covers the simulators related information. And going to the next part, as I have already described, now in the functional verification, we have simulation, and now we have a formal verification. So now, yeah, we have formal verification, but why do we know need a formal verification? So the problem with verification, if you think, right, because since you are having an SOC which is having hundreds of inputs, and you're expecting a behavior to be very constrained. So, but ideally, if you have 100 inputs to your SOC, you really need to verify 2 power 100 combinations, which is practically not possible. So, but simulation, what it does is, if you, as per this picture says, it covers the data points on a scenario basis. For example, specifically, I am going to send data from USB to a memory controller. Then it's fine. You know that scenario, then you verify it. So simulation is mostly driven by the data points which you know. So you drive you data points which you describe, or an architect or a verification architect or a design architect thinks of. So he plans like his SOC should have these scenarios. So that is where simulation is mostly focused. I want to send a packet from interface A and it should come on the interface B, or it should stay it should stay as some control packet to be consumed by a processor or any other interface. So that is, those scenarios are being verified here. But now, are the scenarios only are the scenarios enough? Probably not, because based on the feedbacks which we get from the post silicon, and then feedbacks, bug escapes, all those things, we see that there are certain areas or certain data space or sample space that has been missed by the simulation, which a architect or a engineer couldn't think of. So how do you verify that? That is where we have the formal verification. Since the state space, you call the space at which ideally I would call state space for 100 input SOC as 2 power 100. So that state space has been defined. So now formal verification has a different approach of verifying. So it doesn't really look for the data points, but it tries to form data points based on properties. So it's a different kind of methodology where you write properties based on data sample points. For example, if you see property here, it covers 3 sample points. This property covers 2 sample points. But how do you know? How do you write these properties? So that is where the intelligence of the formal verification tool, of the tool's complexity, how the tool is designed, is being is should be taken into consideration. And also the person who is writing the properties have to be in very close sync with the design architect to get the proper properties to cover the maximum data points, so that your design can be verified. If you see, nowadays, this formal, I don't say nowadays, it has been there for more than 10 years now. So it has gained a lot of importance because it is kind of a mathematical modeling. So the models which the tool uses are kind of mostly algorithmic based. So there is a lot of research going on in this area, where how exhaustively you can cover all the input scenarios for correctness. But the main problem with this approach is it is still applicable only to the smaller designs. You cannot really verify a huge SOC with these things, because the tool will take probably in years to really converge and give you a result. Okay, so that is why we need to know for what we need to use formal verification. So if you see, formal technologies have two two points here. One is equivalence checking. It can be used for equivalence, like give any two inputs. It could be netlist or a design. So are they equivalent? That is one particular application. The other application is where really model checking, where you create a model based on the properties on the design, and you try to get your sample space or the data space being verified. So for that, we will be using some assertions or a properties. They're called an assertion based verification. So which will definitely work as a checker. So if it is if the assertion, none of the assertions are failing, then means your design is perfect. If the sum of the assertion or a property is failing, means at this point there is a bug or an issue in your SOC. Okay, so that is the formal verification. Now we have simulation and formal verification. So now how do we decide which one? So how do we decide which one we have to go? Should we think simulation is enough, or formal alone is enough, or how do we decide between both? That is where the verification planning and verification architect comes into picture. So the verification architect, based on how the design is really complex, he partitions what needs to be tested in simulation, what need to be tested in formal. So based on he writes the scenarios on both simulation world and formal world to get the correct output. And because you know the tool limitations, how much size the tool can take, what all scenarios you can cover, all those things, the verification scenarios will come up with a plan, and you feed into your coverage database. That is where you come up with the complete closure. Okay, now I have achieved 100% coverage, means okay, I have thoroughly verified each and every data path or each and every data point or sample point. So the decision has to be made based on the design size also. Okay, mostly formals are being used for very complex state machines, which has multiple state transitions. Those kind of related designs, formal is used, but other all applications, our traditional simulators are being used because of the simplicity and the model building complexity, which is lesser compared to formal. Okay. Yeah. So going to the next slide. So now we have finished the functional verification part. Yeah, as I discussed the performance verification, and I already told we have SOCs which have huge processor and memory and so many IPs and interconnect designs. So what are the metrics we have? So are all the metrics are being verified? Or the buses, bus utilization? If you take, for example, AMBA bus or an AXI bus, which has a peak bandwidth, is there any lag? Is there any arbiter hung? Because of that, we are seeing a drop in bandwidth numbers, because you are supposed to send 100 Gbps data throughput, but is your design being stuck at serving one particular interface? So that is why your latency numbers are dropping. So all these analysis and metrics are being done in this verification. So we need to build perfect performance models to get proper output from the performance verification. So nowadays this has to be done to get the proper output from the SOCs. Okay, next, as I said, power aware verification. Just like an RTL design is being done using a Verilog or a system Verilog or a VHDL. So there was a standard for power verification or power verification also, because the power design intent is being expressed in a format called UPF, that is called as a unified power format, which is also an IEEE 1801 standard. So if your design is very much sensitive to power power, you need to have your design with this unified power format, so that so all the power related descriptions have been done properly at each stages. For example, at IP level, you need to have a IP level UPF along with your RTL. So describing what are all the voltages, what are all the voltage islands, what are all the retention cells, how the domain, I mean, one voltage domain to other voltage domain crossing happens, how isolation cells have been captured. All these intent we should be also being described in this unified power format. And also now, to reduce the power, there are a lot of techniques like clock gating, power gating, and autonomous and intelligent power entry exit schemes are also being designed. So I've seen certain SOCs where they have a separate controller just for monitoring the power consumption. Like it can be called as PMIC, like a power management IC. So where it intelligently switches on, switches off the power, and then to save the power dissipation or power consumption, and to maintain the power numbers. So a lot of SOCs have been using this. So for all these things, you have to have a power aware verification, which is based on the UPF flow. Okay. Yeah. Going to the next slide. I'm just giving a simple example of how a UPF looks like. You can see the left-hand side. You can create a power domain. For example, VCC 1 volt you have. For example, you can say my power domain VCC like domain 1. Like it has a supply voltage of set to domain supply voltage 1 volt. So those kind of constructs are there. These are being read very well by the VCS or simulation tools, and it can properly map into the design. So you just need to describe your intent. Then the simulation tools can take care of the remaining ones. So you can see what are the power. There is a construct called add PST state. So it's a power transition state. And if you have a retention cell, you can make it as a set retention. And if you have a isolation cell, set isolation, you can describe all of those. And most of these things are all being, if you see, the UPF goes through the synthesis flow, place and route flow, all other flows it goes through. So your functionality, just like RTL, is being taken into consideration. So you don't need to worry that the information described at one level is being lost in other level. So this UPF is carried forward at multiple places within the SOC. So that is where you will have the power intent being properly being put into the design and also being verified at each level of verification. Okay, and yeah, as you can see, logic functionality is extended to support dynamic power switching within the domain. Now, as you know, right, we have domain switching, which will switch from one domain to other domain. So all these things have to be also being perfectly being verified at the logical side. So what if you switch from one power state to another power state, or if you dynamically change the power domain, is there any issues with respect to those? So those are also have to be verified at the logical level. So power aware verification is also pretty interesting and challenging in the latest SOCs. Okay, and now, yeah, as I already described, clocking and CDC verification for multiple clock domain crossings have to be done. Basically, now we have synchronizers at each and every data path. So there will be a lot of clock domain crossings, and then you have those synchronizers being modeled with metastability injection, like a 2-cycle delay flip-flop can have a metastability. Because of metastability, it can land into a 3-cycle delay. So all these have to be correspondingly verified. And also there are a lot of async FIFOs for bigger data bus designs. Now you have a big bus like a 128-bit or 256-bit, or you can take 1024-bit. So now they are those buses, big bus widths are moving from one domain to another domain. So you see that the domain crossings are perfect. So all these we need to do a detailed CDC verification as well to reduce the data loss. So and metastability related issues. Okay, so that is where this verification covers. Yeah, and as I explained earlier, so designs with hundreds of millions, billions of gates. So now we have so much of logic inserted, so many IPs. So now how do we observe where the issue is there? How do we control a particular gate? For example, to divert if there is a particular problem, particular data path has a problem. So we need to have a logic for observation. For example, if you see this observation flop, you just said this based on this mux input, you can observe your SI input instead of from the combination logic, just to see at the output of your SOC that there is a problem or there is no problem. For example, you want to control a particular data path in the SOC. So how do you insert or how do you control it? So there are some pins at the SOC boundary where you can particularly detect any problems, like you can take any problems like stuck at 0, stuck at 1s, or any functional problems, whatever problems you have. So all those can be detected because your SOC has the logic for design for debug or design for test or design for manufacturing, whatever, based on the application or based on the SOC, how it is. So all those also your design has been coded. So now you need to verify those as well, because unless you verify that the intent of the observation flop or intent of this logic is verified, then there is no use once your silicon comes back. And if particular logic doesn't work, then it doesn't really make to have this dead logic here. So verification has to be done for this logic as well. Okay. Yeah. And yeah, now as per this previous slide, yeah, we have seen until here a lot of verification methodologies now. So now the coming to the right hand side is where we have the hardware accelerated related verification now, because all these are simulation models, so they have their own limitations. They run on the machines which have their own limitations, and they have models which have been modeled based on certain assumptions. But now if you want to see how a real hardware really is being is it really working as it is intended? So that is where we come into the FPGA prototyping or emulation models. So if you see, yeah, emulation. If I say emulation, what is really an emulation? Yeah, emulation is the use of a specialist computer which automatically maps the RTL representation of a design to its array. It can be a programmable gate array or whatever it is. So it can map your RTL representation. What is the advantage in mapping this is, now even before your SOC is being taped out, or now you have your design being put into these boxes. So these emulators will come as a boxes. So you have put it into your boxes, and then you can run realistic patterns to see if your design is really capable or if your SOC is really capable of getting the numbers. Okay, one particular, if you take example here, emulation, I'm trying to compare it with a HDL simulator. and then an FPGA prototype. So if you take from hardware debugging point of view, simulator is the most easiest one because you have waveforms you can check. Similarly, those same thing has been put in the emulator also. Emulator also will dump some waveforms you can check, but FPGA prototyping is not that easy, so there was no such facility. You can do software validation on HDF simulator? No, you can't do a software validation. You need a separate interface. You need a separate setup for that. So, but in FPGA prototyping and hardware emulation, you can do emulation. You can do software validation. So these are all the advantages of having your design verified on an emulator. Okay, so as I said, the motivation why we need to do a emulator because of the increasing complexity of the chips. So we need to know what exactly the simulators are they really simulating properly, or is there any assumptions which are kind of masking the real bugs? So that is where we need to do a emulation, and also time to market pressures. So we see products coming every 3 months, every 6 months. So there is a lot of pressure and and there is a lot of uh, pressure to get first time working silicon, and also at with a decent and with a very good quality. So to all for all those things, emulation is really very useful to catch the bugs even before we tape out the silicon. And also they offer shorter compile times. So if you're compiling a particular HDL model, VHDL or Verilog model for a SOC, typically it takes 4 to 5 hours of compilation time itself for a decent SOC. But if you are taking a bigger SOC, it takes much more. So, but these emulators being hardware directly on the hardware, they compile much faster, and they offer you debug and waveform visibility. And also, the emulators are pretty complex. They give you a lot of facilities, so that will help us to debug the problems fast. And last is the software validation. Along with even before your silicon comes, you can also verify your software to see that your design and hardware and software are in sync, and you're getting the proper output. Okay, now these are some of the emulators we used currently are used in the industry. So the top row is where you see the industry standard emulators like Cadence Palladium, Mentor Veloci 2, Synopsys Zebu. So these are all the standard emulators which are used in currently in the industry to get the proper emulation being done. So if you see this, each of them have their own specification itself. So based on customer requirements and the complexity of the SOC, we have to choose, and they also offer per user related simulation boxes are very costly. They offer per box or like time based sharing. So many concepts of using the emulator also, like cloud based, time based. So many features have been there, and depends upon the design size also you have to choose each of them. And also they offer how they have. So all those things are all the driving points for your SOC and how you choose actually. Okay, and as I said, for hardware, software co-design and verification also is very much important for the early validation of your SOC. So if you are parallelly developing the specification for hardware and software, so that is the best case where both hardware and software go hand in hand, and then you can verify them before your silicon arrives, so that by the time your silicon comes and you start verifying, your software is already being stable, and so that you can totally get your SOC working at speed. So this is these are all the various verification technologies and methodologies which modern day SOC companies are being using to get their silicon working. Okay, yeah. So yeah, but no, last but not the least, but there is another set of simulations which have to be done. But why? Because now we have our design which is being going through multiple stages, and a netlist being modified by a lot of place and route tools, a lot of design rule checkers, layout, customization, so many things are happening. Now you get your netlist, which is a netlist which has a timing information also embedded in it. So that is the standard delay format. So you take a netlist, you include your SDF, standard delay format. That is where you get a gate level netlist. So this gate level netlist, what is it different? Because it has the ATPG patterns, that is the design for test related patterns, everything being inserted by the tools, and all the timing corners, everything, STA synthesis tools, static timing tools, everything has been closed. Now you have your netlist, which is annotated delays from the backend, and now you have your delays which are typically seen in a real SOC, like min, max, typical. So still you need to verify that the logically this netlist and this RTL are equivalent. So that is where we do the gate level simulations to verify the design. So if you see the gate level simulation flow, so you get an GLS netlist, that is called a gate level netlist. You do the gate level sim, which is from the static timing analysis tool. You get the SDFs. So you load both of them, and then you run your functional tests. Now you have so many functional tests. And all these functional tests still work on the SDF annotated tools as well. So that is why we do this thing, because of the min-max delays that have been introduced, or the typical delays, whatever has been introduced by the technology variation or by the tools. Still, your tests, whatever you have written at the first step, should still work. So that is where, once you clean all those things, that is where is the final point where you can say your verification has been done and the design can be taped out. So that is the total part of verification. Yeah, just another slide for, if you see, we are doing this many verification stages and this many levels of verification. That is why if you see the total percentage on the x-axis, the time that is spent on the verification varies for most of the chips from 50% to 80%. So it is the most critical path in the SOC design flow. So for your SOC to be to come to the market, or to be sent to a foundry for fabrication, verification is the most critical path, and that is where we are spending enormous amounts of time. Okay, that is what this slide explains. But on and if you see, there is not much change. Even if you take from 2012 to 2018, there is hardly last 6 to 10 years. There is no much difference in the amount of time that has been spent on the verification. So that still remains same, because again, because of I would say technology node, because you're going into 7 nanometer, 5 nanometer, means you are putting in more logic, means you have to spend more time in the verification. Okay, that is what this slide explains. Yeah, and as I said, now we are doing this many verification quality checks. What are the bottlenecks here? The bottlenecks are definitely the simulation time. So if you take as I said, typical one simulation of SOC will run for 1 to 2 days, and compilation will take from 6 to 10 hours based on the SOC size. So simulation time is really a bottleneck to totally verify design. And the next thing is the simulator modeling. So if as I explained, there are three companies which are modeling the simulators. Each of them have their own products: VCS, NCSIM, and Mentor. So each of these three have their own ways of modeling. So that is one gray area or a verification bottleneck. You can say some can be found in one simulator, some can be found in another simulator. So qualification of your SOC on a particular simulator also is kind of a bottleneck. The other thing is the state space. Because of a huge number of inputs to the SOC. Now we have so many number of inputs, so many number of outputs to the SOC. So the state space is enormous. So that as the state space increases, verification as will definitely become a bottleneck. The fourth point is the behavioral models. Behavioral models, why I'm saying is because now you assume that a particular ARM processor or a particular core behaviorally will behave like this. But that model assumptions may not be correct. That is where some bugs can be escaped. The fifth point is the most common assumptions. So when everybody is given a same specification, everybody will not assume the same way. They have their own set of assumptions. So when you're integrating IP from multiple vendors, so these design assumptions are really going to be a challenge, especially for the specification where there is an ambiguity or it's not clearly defined. So that is where that is. And the other thing is non-reusable test bench components. So some of the test bench components which we are using are non-reusable, so that will add to more time because we have to write it again. And the last second is the digital and analog interactions. So now the most of the chip is designed in a digital, but when it reaches the pad level, it converts into analog. So there is a loss, or there is certain kind of a problem within the digital and analog interaction. So that is where verification cannot 100% close on the functionality there. And also, finally, that is the server farm where you are running your tests. They are also a bottleneck because if you are running that many jobs and that many and tests that many hours, so you need huge memory, huge processors. So all these are the real bottlenecks for your verification. Okay, so that is where the real bottlenecks for the verification is. And the final slide, I would like to, if any people who wanted to focus on the research areas, I would like to suggest these four areas where there is enough research work, both from the industry as well as from the university, or a lot of research is being going on these areas. One from the methodology, like how do we define a methodology to verify all these things. So there is a huge potential in methodology area where how a component can be optimized, how it can be adapted across platforms. And also the second one is the formal verification. As I explained, it's an algorithm based, so there are lots of algorithms and it's keep on evolving. I've been seeing from last 10 years the growth in this area. For formal verification is not that great because of various complexities that have been involved. So this is definite. Formal verification is definitely a very core research area where anybody can focus on this.
ಇದು
Okay.
ಬ್ಯಾಂಕ್ ಅಲ್ಲ ಬಟ್ ನೋ ವಿಡಿಯೋ ಹಾಗೆ
Sir, not thinking.
Govind,
Yeah, Chetu.
should I stop?
1 minute, 1 minute. Yeah, Chetu.
You're able to hear me, right?
Yeah. Actually, we came to end, but is your presentation is done or?
No, this is the last slide.
Okay. Thank you. Go ahead.
Yeah.
Is done?
The last point. Yeah.
Yeah. Please go ahead.
Emulation is where another interesting area where the efficiency of interaction between the design under test bench and design under test and test bench can be a very good research area. And the last one is a generic area where a lot of tool development algorithms, routing optimizations can be focused. So with this, I would like to conclude, and if you have any questions, you can please let me know.
Yeah. Thank you, Chetu. Thank you very much. We have few questions and we have noted. I will ask the questions so that we can interact.
Sure.
Next. Yeah. Yeah, Chetu, the first question is Ashok is asking this question. What is the difference between AMBA and network on chip?
Okay. Network on chip is basically it is a huge interconnect actually. The scale of it is much bigger. But AMBA is basically a very basic bus from the ARM. For a network on chip, it can be from multiple vendors, but AMBA is very much specific to ARM, and its scale is very small actually for AMBA. But network on chip is a pretty huge, complex network.
Okay. The next question is from V. Shavali. What is the difference between SOC and NOC?
As I explained, right, SOC is basically a system on chip which has multiple components, but NOC is very much specific to a particular domain like Ethernet or something where you can take it as a network on chip, which is like a cluster of interfaces where you can, it's very specific to an application, but SOC is not specific to any application actually. Network on chip is very specific.
Okay. How the power can be reduced in SOC and NOC?
Actually, there are a lot of techniques in today's world. So most of them use power gating techniques or clock gating techniques, and also certain techniques like isolation of power islands. So it's a pretty huge topic, but for SOC, these are common things.
Okay. How the switching activity is reduced in NOC or SOC?
Switching activity reduced in SOC.
Okay, probably this is out of this discussion.
Yeah.
How to extract the circuit for executed code in SOC?
How to?
Not looking. How to extract the circuit for the executed code in SOC? No, probably their intention is to how to get the code from the working SOC.
I don't know.
Yeah. The next question. How to predict possible electron migration problem while testing? This is post-silicon question.
Our product testing question actually.
Yes, this is post-silicon question. Yeah. What is a test chip? Of course, it is also post-silicon. What is a test chip?
Yeah. Basically, test chip is nothing like as the name suggests, is a test chip which just used for testing. Especially used when we are going into newer nodes. Like if you're going from 7 nanometer to 5 nanometer, you don't know what are the challenges you will face, how much is the yield and all those things. So for those reasons, they put a test chip.
Yeah. In which stage we will be writing the UPF in low power designs for power aware verifications?
Now it's from IP level. It has to be from IP level.
The next question. This question was asked by Dheeraj Talladi, and the next question is by Kalamani C. Dr. Kalamani C. What is the fault coverage?
Basically, you can take fault coverage is any generic term which you see. You have faults in your design. So if you take any fault, basically the concept is to have a fault tolerant system. So once you have a fault tolerant system, so you need to have a coverage for it. That's where fault coverage comes.
Yeah, Chitu. Next question is, when will we use SDF in front end? This
SDF
question
is
is by Dheeraj Talladi. Yeah.
Okay. SDF is used only for the gate level simulations. Other than gate level simulations, we don't use any SDF.
So the next question is, this is the last question. Gururaj Hosamani is asking this question. Sir, what is the accuracy of verification compared to practical implementation of the circuits? Probably the numbers what we see during the functional verification and what is those numbers on various nodes in post silicon chip. What is the difference? Is asking.
Okay. That is really. I mean, we don't really have numbers for one verification, but you can consider maybe probably 70 to 80% as the only whatever scenarios we verify. Still, we end up around 20% on the real silicon. So all the surprise elements around 20% on the real silicon.
Yeah. Yeah, that's all. These questions we randomly picked from the chat boxes, and
Sure.
yeah, because it is not possible to cover all the questions.
Yeah, sure.
So thank you very much, Chetu. Thanks for your very informative session. And in spite of your busy schedule, thanks for giving us time and sharing your knowledge with us. Thank you very much. We are really grateful to you. Okay.
Sure.
So
No
now
problem.
our HOD sir will talk something. Okay.
Hello, sir.
At the outset, I would like to, on behalf of GMR Institute of Technology, Department of ECE, I would like to express my sincere thanks to all the participants from across the various parts of the country for registering for this workshop and attending to the sessions. And also express my sincere thanks to our resource person, Chaitanya Kancharla. He is a IP verification lead in Intel Bangalore, for accepting our invitation and enlightening us and giving more insights towards industry trends and also on research topics. And I have seen the chat box. They are very happy with you, sir. And once again, on behalf of the GMRIT, I would like to convey my sincere thanks to you. Thank you all.
Thank you. Thank you very much.
Yeah.
Thanks, Govind. Thank you, sir.
Yeah. One minute.
Yeah. Thank you very much, Chetu.
Thanks, Govind. Sure.
Thanks a lot once again.
Sure.
Thank you, participants. Thanks for your patient listening. Yeah, let us meet tomorrow by 9:30 sharp. Thank you. Thank you very much. Thank you, Chetu.
Okay, then. Bye-bye.
Yeah, bye.